Okay. So yeah, so during the break we had a a brief discussion or just a little talk. So yeah, I guess I'll just put in a few notes. Okay. So PCA works only for numeric variables. Okay. So you can apply PCA to just the numeric variables and tie them back to the categorical variables. And then there's apparently MCA, which is what was it called? Multiple correspondence analysis. For categorical variables. But I apologize, I don't know enough to offer anything useful about it. But okay, let's see. So here we are. We're doing PCA. We looked at. I guess I'll save these and put this in our notes. Okay, so PCA in class. In this textbook, Handbook of Statistical Analysis Using R, they have an example of PCA using for heptathlon data. Okay, and so there were 50 warnings. More warnings. Oh, it was not a graph. Okay, that's fine. All right, so so the heptathlon, it's an event in the Olympics where it's like a track and field thing, and the athletes, they compete in like 7 different events, and then they score whatever this much on the hurdles and this much on. This is how far they threw the javelin and the hammer or whatever. And then they get some kind of score, and then and they compete. And so the raw data is 7-dimensional, right? Because there's seven events, and so our raw data is 7-dimensional, and yet we have a goal to say this is the best and this is the worst, and we want to be able to. We want some way to differentiate strong athletes from weak athletes using using a single metric. So we need a way to combine the raw scores from the 7 events into a single number that kind of gives you your overall performance for all 7 events. Okay, so this is an example where we need to go from 7 dimensions down to just 1 dimension and still manage to capture the structure in the data, showing this is the strongest performer and this is the weakest performer. Okay. Okay, we have 7 events, and we get scores on the 7 events, scores / times on all 7 events, and we need to go from 7 dimensions down to 1 dimension. Okay, and maintain the structure and the data that differentiates a strong athlete from a weak athlete. Okay, so that's what we want to do. So PCA is a good example for this. Okay, so if we take a look at heptathlon, this is what we have. We got hurdles, high jump, shot put, the 200-meter run, long jump, javelin, and 800-meter run. The Olympics already have a way to score the athletes based on these things, so they already have a system to do this. But it's kind of an interesting exercise to see if we can get something that creates a score as well. Okay. We're going to have to reverse some of these things, hurdles and 200-meter run and 800-meter run, because in all of the other things, higher numbers are better. Okay, high jump, you want to jump higher. Shot put, you want to throw it farther. Long jump, you want to jump farther. Javelin, you want to throw it farther, right? But then the hurdles, the runs, you want smaller times. Okay. So I think this is from which Olympics were these from? Okay, so it's from the 1988 Olympics, and the gold medal winner was Jackie Joyner-Kersee from the USA, and then GDR, what's that? East Germany, I think, back in 1988. And then, okay, so anyway, this is the score. Well, so we're gonna do just a few operations to kind of clean up our data. We're gonna just take the hurdles, 200-meter run, and then just reverse them. So we're going to do max minus each person's run or thing, okay? And then, and so if we take a look at this, so after we clean that up, we've turned everything into kind of the slowest, how far ahead was the person from the slowest runner. Okay, so for the 200-meter run, Joyner-Kersee was 4 seconds faster than the slowest, and for the 800-meter run, she was 35 seconds faster than the slowest. Okay, something happened with this person from Papua New Guinea who was just way slower than everyone else. Okay, and so we might just be curious what if we did a plot. This is a pairwise plot of all 7 variables, and they're all numeric, and so we can create scatter plots, and we're trying to find some structure. We see that there's positive correlation between a lot of these variables, right? Like people who ran faster also happen to throw the shot put farther, and we're going to see pretty strong. We got strong correlation between the long jump and also the 200-meter run and things like that. Okay. Other things, the correlation isn't as strong. There's also, we can see in these things, there's one observation that's just like way lower than everyone else, and so we might want to remove this, okay? Because we want to come up with some kind of system that is appropriate for, I guess, Olympic level athletes, and not one that's going to differentiate, I guess, lesser performing athletes from the thing. Okay, so we're gonna remove you know, this person here, and so we'll remove the outlier, and then so now just kind of looking at here's the correlation values, and then if we also look at the so this is looking at the same plot again without the outlier, and so, you know, probably the strongest correlation will be between long jump and 200-meter run. Some of the other variables, the correlations aren't as clear, okay, but we still want some way to do this, okay. So we can use there's a package called there's a few packages in R that do principal components. There's PRComp, printcomp, and then facto -R, okay. So, and I'll just show this here, and using PRComp, and you can print the summary, and this will be the kind of the variations here. Let me also just kind of show if I do library facto -R, and then we'll do heptathlon heptath. All right, I'll call this hep PCA, and this will be PCA of heptathlon minus the last column. Okay. All right, and so everything, you know, our first two kind of says we're going to look at hurdles and 200 meters as kind of our first principal component. We'll look at the hurdles and 200 meters. Maybe this is like kind of the speed running. And then the other thing that differentiates will be, you know, high jump versus 800-meter run. So this one will score. I'm not quite sure, but basically, we only want to look at the first dimension here, because we want to get them down to just one dimension. And this says, you know, the things that are going to be most important as far as deciding who's kind of the best athlete will be the hurdles, and the 200-meter run will probably be the most important ones. And then as far as the other thing goes, you know, long jump and shot put are also predictive. Javelin seems to be the least predictive one here. If we false. No. It's the okay. And so looking at this plot, we can also see Jackie Joyner Kersey is our strongest performer, and then John Bamer. These kind of bunch them all together. You know, there's some. These people are quite close together as far as just looking at the first principal component only. Let me we can look at just the first weighting, which is going to be the result of this. And if we project everything based on this, we can just kind of plot the actual score versus when we projected it down to one dimension. So when we compressed our 7 dimensions down to 1 dimension, okay, we get the values here: heptathlon PCA, okay, $X1, I guess. And if we compare that to the Olympic scoring method, we see that they are almost perfectly, there's a perfect linear relationship there, okay? Meaning that the system that the Olympics have set up for determining who's the best and who's the weakest is a pretty good system, because our system of just trying to maximize the variation that we've identified between the athletes basically comes up with something almost exactly the same, okay? There's a little bit of maybe disagreement right here in terms of, these athletes kind of in the middle, but as far as, who's the best and who's the worst, there's very strong alignment there, okay? So that's a good sign here, okay? And anyway, that's what we have, okay? I want to just kind of show maybe like I don't know. In my mind, this is kind of fun, and so this is not done in real life, but it also kind of shows the effectiveness of principal components analysis here, okay? And so let me just close this out here, okay? I'm going to load up, let me restart R. Okay, and clear everything out, okay. So I'm going to load this package called Imager, and what this does, it allows me to load images into R, okay? And so I have, whoops, this is, okay, so I have a JPEG of Audrey Hepburn, and it is 634 pixels by 791 pixels, okay? And when you load this into the matrix imager, it brings it into this high dimensional array, okay? 634 for the number of pixels, 791 for pixels for the height, width, height. This is 1, meaning for frame 1, it allows you to kind of load in GIFs that have multiple frames. And then 3 is for the color channels, red, green, and blue, okay? This is a black and white image, so red, green, and blue will all have the same values, okay? So we can just kind of flatten them all and make gray, okay? So I'm just going to take, just capture 634 by 791, okay? And that's, so odd will be just a single matrix with 791 pixels and 634 pixels. And if I plot this, this is Audrey Hepburn from Breakfast at Tiffany's. Okay, so this is the original image, and you can look. We can look at the actual matrix. Okay, so this is just represented as a big matrix that has 791 rows and 634 columns. So I can just say, let's look at the first 10 rows and the first 10 columns, and we can see they are just a whole bunch of values, okay, for things that are, I think they've scaled them from 0 to 1, okay, where 0 represents black and 1 represents white, okay? So I think this is this top left corner here, so we have values that are close to 0. And then if I go to, I guess, right around here, which would be, what, the 200th row, maybe the 250th row, and the 150th column. Let's just kind of see if I go to 250 to 260 and 150 to 160. So I think that's going to be somewhere around here. I think we should have values, values that are close to 1, okay? So these are values that represent white. So, in that the first column, we had values that are pretty close to 0 because this is a pretty dark area of the picture. And then if I go to kind of 250, 150-ish, somewhere around here in the image, okay, you can kind of see the pixel values for each of these things. This is a pretty bright area of the image, and so these have values close to 1, okay? And so we want to, what we're going to do is we're going to just try to do principal components analysis here. And I'm going to just go ahead and do this kind of the manual step way, all right? So first we're going to we have 634 columns, okay? And I'm going to go ahead and I'm going to just find the column means here. And so if I do Audrey means, I've got 634 column means, and I'm going to go ahead and I'm going to center this matrix, okay? And so if I can just test to see if all of the column means of the centered matrix, if it's the same as 0, and it says indeed it is, okay? And if I plot as.image transpose of Audrey centered, as C image, okay? This is what it looks like, which it feels weird. It just feels like a streaky version of it. But what we've done is we've subtracted the mean of the column out so that the average of this column, if we took all of these values, the average of this column will be 0, okay? And so if somehow we took every pink pixel in one of these columns, it would average out to being 0, or whatever the kind of the center value is. And so where you have a bright white area, there's going to be a kind of a darker black area, and over here where it's kind of all drab and gray, this entire column of pixels is kind of drab and gray, is what I guess is what's going on here, okay? But anyway, I'll go ahead and I'm going to find the covariance matrix of our centered thing, okay? And so our covariance matrix, if I ask for the dimensions of this, it's 634 by 634, because we had 634 columns in our original data, okay? And then I'm going to ask for the eigenvalues of our covariance matrix, okay? And so if I look at that, I have 634 eigenvalues and 634 eigenvectors. Each eigenvector has 634 values in them, okay? So what I can do is I can say, you know what, I don't want all 634 principal components, okay? So far when I find all the eigenvectors, I have 634 resulting ones, and this would capture all the variance that's present in the original image. But what I can do is I can say, you know what, I only want 50 of these, 50 out of 634, okay? So we're reducing the kind of the dimensionality of our data to be, less than 10% of the original matrix, okay? So I'm going to say I only want to keep the first 50 eigenvectors, okay? And so here, PC50 is 634 by 50. So we've reduced the size of our matrix considerably, okay? And so I'm going to take my original data, Audrey centered, and multiply it by these 50 weight columns. And so this will create our projected data. And so our projected data has 791 rows and 50 columns, okay? So in our original matrix, we have 791 rows and 634 columns. We've now projected this down to 791 rows and only 50 columns, okay? It does not make sense if I try to plot this of my projected thing, okay? This doesn't look like anything, okay? Because what we've done is we've projected our original data down to just 50 columns, okay? And the principal components themselves, while they capture a lot, this is supposed to capture a lot of the variation that appears in the original data, we can't make sense of this. In order to make sense of this, we have to take our reduced data and then undo the projection back into 634 columns, okay? So it's like we've compressed it down to just 50 columns, but we have to undo that lower dimensional projection and recreate something back into a higher dimensionality, okay? It's kind of like when you see an image on the screen, like you're watching a movie, inside your brain, even though you're viewing only 2 dimensions, okay, inside your brain, it's easy for you to reconstruct what that object looks like in 3 dimensions, right? So even though you're only seeing the object in 2 dimensions in your brain, you can reconstruct it into 3 dimensions. Likewise, we've projected it down to 50. We need to, in order to kind of make sense of it, we need to project it back into its original form, okay? So to do that, so I'm going to take my projected data, which is the small version, 791 by 50, and multiply it by the transpose of the kind of the operation we did to project it, okay? So this is going to be reconstructed, okay? And so Audrey reconstructed is back to 791 by 634, okay? So it feels kind of silly because we started off at 791 by 634, but what we've done is we've reduced it down to 50, okay? And then from those 50, we were reconstructing it back to 791 and 634. So effectively, I mean, we don't actually do any kind of image compression this way on the computer, but if we wanted to, we could, in that we could take the original image, project it down to only 50 dimensions, okay? And then we can transport the reduced matrix, okay? Well, we would have to transport, there are 2 pieces we would need to transport in terms of sending. We would send the 791 by 50, and then we would send PC50, which has the operation to undo the transformation, okay? Oh, and then we would also need to add back the column means, okay? So there's 3 pieces that you can send, but these 3 pieces together are a lot smaller than the original data. The original data was 791 by 634. This one is 791 by 50. This one is 50 by 634. And then the last one is just a vector of 634. So it's the total amount of data is a lot smaller here, okay? And so so we've done this. We have to add back the means, okay? And so our reconstructed data looks like this, okay? And so I'm gonna show this image, okay? And so when we do this, this is the image reconstructed after reducing it down to just 50 columns of data, okay? And so we can see that we have lost some information because the original image, here, let me delete this plot, and then let me delete this streaky one. Okay, so this is the original image, okay, where we have the original 791 pixels by 634 pixels, okay? We have the original matrix of 791 by 634, and then if we compress it down to just 50 components, okay, we get something that is not as sharp and clear. We've lost some information, but it maintains the structure that was present in the original data. Okay? I don't know. I think that's kind of neat, right? So all we've done is we've treated the image as this high dimensional data set, and we've reduced it down to a lower dimensionality, in this case 50 dimensions, okay? And then we used those lower 50 dimensions and reconstructed kind of the original 634 dimensional data. And yes, we've lost some information, and the picture is now kind of blurry compared to the original, but anybody who sees this would recognize immediately what this is a picture of, okay? And so, we could argue that, we've maintained the structure. And so so here I just kind of created a loop that shows us keeping only the first principal component, and then keeping two principal components, and then I just kind of jump up, keeping 12, 14, 16, 18, 20, up to 200 and 500 principal components, okay? So if I do this and I create all of these images, it takes a little while to run, okay? Okay, so the one we looked at, this is so that's with 150 principal components. Let's see. With okay, so this is what we had. This is with 50 principal components. Let me just kind of. So if you only keep one principal component, you lose a lot of the structure of the data. Okay, you can't recognize what this is. Here, if you have keep two principal components, we're keeping a little bit more data, and with three, we're starting to be able to reconstruct some of the variation that exists. Can I zoom? And I guess it keeps resetting here. Let me see. Okay, so this is with 2. Here's with 3. 3 to 4 is not. It adds a little bit, adding a 5th dimension, and then here's a 6th. And going from 5 to 6, I don't know. Suddenly you can see something that looks kind of like a face. Okay. And as we add more and more principal components, here's 7, 8, going to 9, and 10, and 12. Here's 14, here's 16. And I feel like at this point, you have an inkling of what this picture is, right? So that's with 16 principal components. And then as we add more, here's with 20, 25, and with 30 principal components, the image is starting to get more and more clear, okay? Here's with 35 principal components, and as I add more, here's at 50, 70, at 90 principal components, it feels like we have a pretty good representation of what the original image is, okay? And as I add more, the image does, maybe it just feels like we're increasing the contrast of the image. And the difference between 150, 180, 210, I can barely tell any difference between adding an additional 100 principal components to looking at the image, okay? So, as we reduce the number of principal components, we lose a lot of, we lose information, okay? But I don't know. This almost feels like in some terrible TV show. They talk about enhance, and you get the image, and it's like, or it's kind of like, what is the computer doing in terms of like enhancing the image, and then suddenly you're like, oh, that's great, but the information is lost. Yeah.
With PCA with just one, is it basically trying to like use one column to describe the entire picture? That kind of
Yeah. It's using one vector. It's basically, so each row. So PCA with one has only has 791 values in it. Okay, and it says each vector gets each row gets one value, and that one value will determine what that row is supposed to look like. And it's trying to describe the entire row of pixels with a single value. And when you do it, it doesn't do a great job, okay? Now we can use 5 values to describe an entire row of 634 pixels, okay? And I don't know. At this point, we can use 10 values to describe an entire row of 634 pixels. And, so this is going to be, 791 rows, 10 columns, and we can describe it kind of like this. This is about as good as we can do with 10 different numbers to play with. And, when you get to something like 50 or 70 values, you can do a pretty good job of reconstructing all 634 pixels, even though you're given only 50 or 70 numbers to work with. Okay, so this is it's again on a practical level, image compression is not done this way. Theoretically, it could be, and you would have to. It's probably not done this way because it's going to be computationally expensive in terms of like, yeah, you can transmit less information. Okay, you can transmit a smaller matrix and the other matrix, 2 small matrices plus column means to reconstruct the original thing. But the computer has to multiply these big matrices and create this new thing just to create the image. And so, on a practical level, it's not done. JPEG compression is done using wavelets or something, and apparently that's easier to do. But theoretically, it can be done. Kind of on a practical level, as far as PCA, a lot of its usefulness comes in making it easier for us to work with high-dimensional data. Maybe you have high-dimensional numeric data, and trying to do some kind of machine learning thing on the high-dimensional data maybe is too difficult for the computer. So you can reduce it. You can use PCA to reduce the number of dimensions while still maintaining the structure that exists in the data, and using your machine learning tools there to kind of come up with predictions and whatnot. Okay. But of course, at the end, you still, if you want the original values, you have to do the reconstruction. You have to multiply it by the transpose to get the original thing back. I don't know. Okay. Do you guys have any questions on any of this stuff? This is just a very, very, very brief introduction to kind of the topic of dimension reduction, PCA being kind of the primary tool there. And yeah, apparently there's multiple correspondence analysis for categorical variables, and if there's kind of a whole field called factor analysis that goes into dealing with high dimensional data there. Okay. All right. Well, we can call it a few minutes early today. Thanks for coming out, you guys, on a Friday night, and enjoy your weekend. And well, those of you who get Monday off, and if not, we'll see you guys. I guess in I don't know, what's that 12, 13? I don't know, 12. I can't count. Whatever it is, not next Monday, but yeah. So we'll see you guys in, I guess, 10 or 11 days, something like that. Okay, have a good night.
Wait 1 second.